Oh,
Okay, so Lucas Kramer is a PhD student at Minnesota, where he is doing research on attribute grammars. But he's not talking about that today, I think. Instead, I think he's talking about work he did at Google, where he worked on adding generics in the style of GHC.Generics to Bluespec. Lucas, please take it away.
all right. Can you see my slides?
We can indeed.
All right. Thanks, everyone. Yeah, so I'm Lucas. So a bit of background. So Bluespec is a hardware synthesis language, a high-level hardware synthesis language, where you can, for basically designing circuits, essentially, for designing processors or whatever kinds of hardware you'd like to specify. And it's a language that's heavily based on Haskell in a lot of ways. It's actually some of the same people that worked on early versions of Haskell also worked on Bluespec originally. Uh, there's a Now they have a system Verilog inspired syntax for it that it basically uses the same sort of Haskell inspired AST, and the Haskell syntax is still supported. And it's been around for quite a while. It was started about 20 years ago, but just recently open sourced in 2020. So there's more details on Bluespec if you are interested. There's a tutorial last year at ICFP by Nikhil that you can check out if you want. And my project at Google internship last year was implementing a generics feature, which was merged upstream in March. So it's now free to use for hardware designers that are interested. Also, just for the purposes of the slides, anything that's in blue is Bluespec code. Otherwise, it's Haskell. The two look quite similar, as you'll see. So a little more background on the Bluespec and some of the features that we're interested in. So Bluespec's a two-level language. So there's elaboration time when hardware is designed, basically in terms of modules, and these modules get composed together, and this can be done programmatically and sort of generating the how the hardware design is, the different parts are hooked up. And then there's also another level, the hardware when it's actually being simulated or running in a physical chip, doing the logic part of it. So Bluespec also describes hardware in terms of basically we have rules that fire as atomic actions and interface methods that describe the interfaces between modules and how they are connected to each other. And values have implicit conditions attached to them that control when the rules can fire. And Bluespec also has some primitive, some very basic dependent types features. We can have numeric types, which we call kind pound for like number symbol, that let us have things like, for example, a vector of n 8-bit integers as a type. And also, familiar, Bluespec has records, which are called structs in the language, and also algebraic data types, which are just like Haskell algebraic data types. We also want to be able to have hardware designers use these algebraic data types, and the type class system is really what enables this. We have multi-parameter type classes with functional dependencies, amongst other features that we're interested in. So type classes in Bluespec, there's a lot of different ways that we use type classes. One example is the bits type class. This basically is specifying for any type A that has a serialization into a bit value, where a bit is a primitive type that's parameterized by n, which is the number of bits required to represent that type. So the bits type class has the pack method that packs a value into a bit vector, and an unpack that takes a bit vector and turns it back into the value. And the n, so it's a multi-parameter type class. So A is the type that we're serializing, and n is the number of bits required to represent it. And the functional dependency specifies that A determines n. So we determine the number of bits based on the type that we're interested in. Also, there's type classes for pretty-praying things. There's two different syntaxes for Bluespec, as I mentioned. So there's two different versions of a show type class. We also sometimes want to initialize structures with default values, or there's also some type classes that are used internally in the compiler, like prim deep seek cond, which is used for composing together, basically lifting the implicit conditions of a value, determining when it's ready for the compiler. And what all these type classes have in common is that they can have lots of boilerplate instances that we write for almost every type in our design. So the Bluespec compiler supports deriving type class instances just like Haskell. So some of the default type classes like fshow, eq, ord, and also bits all have derived implementations where you can just say deriving some list of type classes on your data type declaration. But adding new derived type classes means that we have to modify the compiler, which isn't optimal. So for example, we have the default value type class, which has a single method that's just a value of type A. And we have an instance for integers where the default value for integer is 0, or integer is a primitive type. But if we have some data type foo, we basically want the default value for any data type to be just the default values for the first constructor with applied to the default values of all the constructor arguments. So we want to generate this instance default value foo where we just have foo applied to default value, which requires this big ugly blob of Haskell code in the implementation of the Bluespec compiler just for this one very simple instance. And this isn't even the entire thing. This is only for data types. And the question is then, what if we want, or what do we do if we want to customize the derived behavior? For example, if we, instead of the default derived bits type class, what if we now want to have a byte-aligned version of bits? Or there's many other examples of this where we want to sort of slightly tweak how the driving happens. And we don't want to have to modify the internals of the compiler. So one option that we thought about was doing something along the lines of template Haskell, where we can basically programmatically generate code at compile time in the Bluespec specification. And we actually already have a compile time evaluator for purposes of static elaboration. So it would be conceivable to just build on that and use that for doing a template Bluespec. But there are a couple of significant issues with this. So one is that template Haskell is nice because the GHC is already in Haskell. We have ADTs representing the abstract syntax of Haskell. In Bluespec, if we want to have template Bluespec, we somehow need to expose Bluespec's AST in Bluespec rather than Haskell. Another issue is with quasi-quotation. If we want to actually sanely specify bits of Bluespec AST in our sources, we somehow need to port a parsing library into the Bluespec hardware language, which seems a little, it could be doable, but it's a bad power to weight ratio, as some would say, for a lot of work to do this effectively. Another option is doing something along the lines of GHC.Generics, where GHC.Generics is basically a generic approach to deriving type class instances, where we have this generic type class that specifies a representation type for any type A, where it's sort of in terms of basic sum and product types, and we have a way of converting from any value to its representation value and back in the other direction. So then we can define implementations for type classes on this representation and be able to automatically get an implementation for any type that can support this. And this does cover most of our desired use cases in Bluespec. Just for completeness, we also did think about scrapper boilerplate, doing something along those lines, which is an approach to doing generic folds and traversals. Most of you probably familiar with it. This is maybe a little less well suited to implementing like overloaded things like bits. Another more subtle issue is that Bluespec doesn't have the same kind of rank 2 quantification we'd need for a lot of these types in order to write. Like the type of G-fold L, for example, or so we thought. I'll get back to that in a minute. So based on this, we decided to implement something along the lines of GHC.Generics in Bluespec. So now talking about a little bit of the design for generics. So we have the generic type class in Bluespec here. We don't have type families in Bluespec. So instead, we just use a multi-parameter type class with a functional dependency, which is basically equivalent. So we have the generic of A, and for any type A and R, there's an instance. If R is a generic representation of A, and the type A uniquely determines the representation type. And we also don't care about types, generics for types this kind star to star for now. So this just means we don't have a generic one type class like in Haskell, and we also don't have to have an extra type parameter floating around on all of our representation types, which is nice for a few reasons. So for example, here looking at the representation type for a struct. First of all, we're not following Haskell's naming convention. So I have this, if a struct foo on the left, the representation type is shown on the right with the metadata abbreviated because it's very large and messy. So we're not following Haskell's convention. So instead of K1 or Rec0 for like the sort of bottom level concrete types and that are the members of the struct, we just have conc for concrete. Also, meta instead of M1 is what we use for tagging types, representation types with their metadata. Another really nice thing and really interesting is Bluespec has inductive tuples. So we have basically a primitive pair struct that a tuple type desugars to. So instead of a custom colon star colon constructor for product types, we can just reuse tuples, and basically is in terms of these primitive pairs that we can write the instances in the same way. For data types where we have some types, we also reuse the either type, and because once again, we don't care about kind star to star, so we don't need this extra type parameter. So we might as well just reuse either. So we have something in terms of tuples and eithers and for our representations. So now talking about our metadata schema slightly. So meta tags the generic representation with info about constructor names and field counts and positions. So we already have numeric types, so of kind pound, which are for doing things like the size of a vector or something. So we already have that. We added a string kind specifically for doing generic metadata for doing the names of fields and the names of members and like the package name and data. Metadata, another interesting thing is that we are including in the metadata, or the metadata type for data, a tuple of all the type constructor arguments that were given to the type, which we needed for a couple things. It lets us do stuff like, for example, if we want to print the type as part of our generic representation or part of a generic implemented type class, or do a type name mangling for generating C code, which is a cool thing we did. I'll mention later. This spec also doesn't have data kinds, so we have these separate metacons named and metacons and non-constructors instead of having a single one that is like promoted to the kind level like we do in Haskell. And also we don't have zero constructor data types, which is just a little bit annoying. So we have a bunch of dummy constructors that never get used for all these data types. Another thing Bluespec has that's quite important in hardware are these fixed size collection types. So we have vector and also list_n, which is a fixed size list versus vector is basically more of a type statically typed size array. So these are important things that we want to handle generically. So we need some sort of type representation for them. So my first try at this was doing some fancy instances that basically turn a vector into a chain of tuples, basically or as a product type for all the elements, which didn't work out. This would have been nice. It would have allowed us to, if you have a generic implementation for anything that's for a product type, we can just have this generic implementation work for collections then. And this unfortunately gets kind of messy, and I eventually gave up for a few reasons. But the alternative that we came up with was using just vector itself as the generic representation for these fixed size collections for vector and list_n. So basically we have an explicit instance for a vector and list_n then that just have as their representation type a vector n of the concrete elements, and just using the existing from and to and for converting between list_n and vector. So so now an example. This is what you actually write for doing the generic implementation of something. So prim deep seek cond, which is so basically lifting these implicit conditions on values is basically the simplest one, the simplest thing we've implemented with generics. So basically it has for a type A and B, it basically will lift the implicit conditions of some of the first argument and include them in the implicit conditions of the second argument. So the representation type for this, sorry, the generic type class version has this basically is yes overloaded for the representation types. So we are just ignoring metadata. In either type, require a instance for both of the operands, and we just call recursively. Same thing for a tuple for a sum type. Unit basically is for empty tuples, just ID, and concrete types. Then we recurse back to the non-generic prim_deep_seq_con type class there. So then the question is, how do we actually specify the instance for a type class in terms of the prim_deep_seq_con's generic implementation? So the Haskell approach for this, if this were Haskell, we basically would write something like this, where we have the default instance signature or the default class type signature extension, where it lets you write a more specific type signature for a default implementation that only applies if there's a the default implementation is only valid if the more specific type signature can be type checked. So here we would have a default signature where we have the generic instance and the prim_deep_seq_con prime type class, and the default implementation calls from, and then we explicitly define instances for the foo and bar types for prim_deep_seq_con. Unfortunately, this isn't an option in Bluespec. We don't have default instance signatures. And also the prim_deep_seq_con type class is something that's used internally in the compiler, and we'd like to avoid having to write, well, somehow still specify that there's an instance that exists for every type. So the alternative that we take in Bluespec, it basically allows what we refer to as default instances, which is basically a combination of the flexible instances, overlapping instances, and undecidable instances extensions in Haskell. So we can just write basically a instance of prim_deep_seq_con A for any type A, and this will apply if there's not a more specific instance for prim_deep_seq_con. And this has the needed context, and we can use this for the generic implementation. And also an interesting anecdote, we found a bug actually with handling mutually recursive instances in the Bluespec compiler, which we had not previously exercised seemingly prior to adding generics. Also, something to note on this way of doing things is that there's no good way of saying we don't want a generic instance for some type. For example, bits and EQ aren't as nice with generics because there's some types where we don't want an instance for those type classes, but writing a sort of default signature means that there's always an instance that exists. It's just that instance resolution might give some annoying error messages if it turns out the prim_deep_seq_con prime or generic type class doesn't have an instance for that type, if it's for some primitive or something. Another interesting thing, so I did slightly lie earlier. Bluespec actually does support rank 2 types, as we discovered after not realizing that these were a thing in Bluespec for some time, but only in struct and interface fields. So, for example, we have this interface for fold FIFO. It's basically a first in, first out structure, a queue for hardware. And it has a fold method that you can fold over all the elements that are currently in the FIFO, besides just the general NQ and DQ and all these standard things. So the type B, which is basically the type of thing that we're folding into, is not in the type of the fold FIFO interface. So this is a rank 2 type with a sort of implicit for all there.
Just so you're aware, we're well into question time by now. So.
Oh, I was told I had 22 minutes for it. Sorry.
Yes.
Sorry about that. Okay, I'll try to wrap up here. So the issue that comes up here is generic. We somehow have to write the generic representation for this. And this is the instance you may write where basically now we have a conc field with the type B shows up here in the generic representation. Unfortunately, recall due to the functional dependency, the type A actually is determining the R representation, or it must fully determine it, which does not hold because B is now polymorphic in the representation. So yeah, we have to fix this because we use generics for these internal type classes. So our solution to this is we add another, basically we generate wrapper structs for anything that has a higher rank member in it. And we have this alternative conc poly thing that says that this is a higher rank 2 member. Yeah, and then we don't lift implicit conditions from these. Yeah, we also implemented generics deriving in the Bluespec compiler. And finally, we use this for a bunch of really cool things. One being generating C code and doing the equivalent for doing a serialization and deserialization. And this lets us communicate generically with a equivalent generic implemented encoding and decoding module and hardware between a host and device application. Yeah, sorry about going over.
You're fine.
Yeah,
Thanks very much.
Thank you.
Let's thank the speaker. Thanks very much. I always enjoy seeing stuff about generics. We have time for maybe 1 or 2 questions. There's one marked as silent, so I guess we should not bring that up in here. Any other questions? I actually have a question myself. Actually, I have 2, but let me ask one first. So I'm not a Bluespec expert, but my understanding is that it has like pure functions, but it uses to model sequential circuits, and then it has this thing called actions, which are like updates to registers, things like this.
Mm-hmm.
Is it possible to write like generic actions?
To do what?
I don't know. I mean, maybe write to like I don't know, some generic way of updating a register depending on I mean I don't know what you might want to use it for, but I could imagine that there are some things that you might want to do.
So yes, I have used generics for doing some things with like actions involved. Like for one thing was doing basically going from implementing a hardware module for doing this sort of credit counting message exchange thing, which more going into more detail on this project, where basically we're doing this flow control and you just specify the message channels you're interested in by just writing a struct that's the interface for your message interface, and using generics from that to synthesize a module that has actions and rules and things inside of it for doing different updates. So yes, I think is the answer to your question.
Okay. Yeah, I'm not sure how it works with the type system. So I mean, yeah, fair enough. Any other questions? I guess there's no. Oh, I see. Okay, sorry. All right. He says silent question. Okay, I misunderstood what he meant. Okay, there's a question from Artem. Let me bring it up on the stage here. Silent meaning he doesn't have any audio. Have you thought about getting deriving via in? May ease some challenges with deriving instances.
I believe that was something that I considered, that we considered and did not have time to pursue. But that is a reasonable approach.
Mm-hmm. Yeah, I mean it's very powerful in Haskell. So.
Mm-hmm.
And while we're on the topic of more powerful stuff, I mean, did you consider you mentioned I mean, scrap your boilerplate stuff, but there's also different ways of, doing generic programming. For example, like sum of products. But I guess maybe Bluespec's type system is not powerful enough to express it. Is that maybe right?
I mean, that's in terms of sum of products. I don't. I mean, that's basically what our representations are.
Well, this is binary sums of binary products as opposed to n-ary sums of n-ary products. So you don't have to do this arbitrary nesting thing. Like in this case, it's like a data type is a sum of a sum of a sum rather than a sum of a product. You know what I mean?
Oh, I see. Yeah. So I mean, Bluespec's like higher rank, or sorry, like numeric types and like sort of the more dependent features of Bluespec are kind of limited. So I mean, I'm not sure. So I mean, this is sort of, I guess, along the lines of what we have with dealing with these fixed size collections. It's basically that is a product of n types, but there isn't anything for a more direct some type, I guess. I have to look more into what that is in Haskell. That approach you're referring to.
Well, I might be a bit biased because I'm one of the authors on it. So.
Okay. Okay. I'd be interested to read about it.
Fair enough. Okay. All right. If there are no more questions, oh, right. Okay. Yeah. I mean, Adam remarks that Generics SOP doesn't need data kinds, for example, so that yeah, Bluespec type system might not be powerful enough. Yeah.
Yeah. Bluespec does not have data kinds. We kind of worked around that already for doing metadata, but it's right. A little bit messy.
Right. Okay. Well, let's thank the speaker again. Thanks, Lucas. It was very interesting.
Thank you. Thank you, everyone.
I will remove you from the stage, and then I think Ning has some closing words for us.